Hey, what's up, guys? This is episode 3. Can you pass a MIT PhD qualifying exam? So, for those of you who don't know, when you're admitted as a graduate student, you actually have to pass a qualifying exam to become a PhD student. And this qualifying exam varies from department to department and from school to school. But here in the Department of Mechanical Engineering, you have to take 3 subject exams of your choice and also present on your research exam. Now, you take those 3 subject exams typically within a day or two, and then after that, you do your research presentation. And you need to pass 2 of the 3 subject exams as well as your research presentation to become a PhD student. So typically people study for anywhere, I think, 10 to 16 weeks for this exam. And each week they study anywhere between 20 to 40 hours for this exam. So today I actually have exam problem in thermodynamics. Now in thermodynamics, the way it works is that you need to get a 7 out of 10 to pass. And on the day of the exam, you're alone in a room by yourself and given 30 minutes for you to solve the problem. So hopefully in the 30 minutes, you look at the exam, you panic because you're like, shoot, this is a really long problem statement. You have no idea what you're doing. You ask God for help, and hopefully God can give you some inspiration so that within the 30 minutes, you can write something down. And after the 30 minutes is up, you look all sad and stuff because you don't really have much down and you're probably going to fail. Or you think you're going to fail. So then you're escorted to another room. And in the other room, you're in a whole big room on a whiteboard, a chalkboard, or even you're sitting in front of a desk with a piece of paper, and there are a committee of professors surrounding you, and you're supposed to present your solutions to them. So professors vary from person to person. You know, some professors are really helpful. They see that you're struggling, and they're trying to lead you towards the right solutions. These are the best type of professors. There's some professors who are really bored. They're honestly sleeping in your exam. There are also some professors who are more, I would say, aggressive. They make you doubt your assumptions and your answers. And by making you second guess yourself, they're almost kind of wanting you to trip up and fail. But it's up to you to convince them that you're ready to become a PhD student. So after 30 minutes of examining you, your time is up, and hopefully you're able to get a 7 out of 10 on the exam. And typically after the exams are over, the next day you'll find out whether or not you passed or not, because the committee actually formed and they look through all the students and evaluate their performance to see if they should pass or not, based on the individual subject requirements as well as how they did on the research presentation. So hopefully you pass and you can go out, drink 1 or 2 or 20 beers to, forget about the experience. Or if the worst case situation, you fail. So one of 2 things can happen when you fail. 1, you take it again and hopefully you pass the second time. Or 2, you do really poorly the first time that the committee decides to actually not let you take the second time, so you're forced to leave the program, which kind of sucks. So let's see, guys, if you can actually pass the thermodynamics exam. This is actually an original problem statement. Let's see if you guys can actually solve it. Alright guys, so this is exam. It came from the 2013 May qualifying exam in thermodynamics. If you guys want to pause right now and read the problem statement, please do so. Alright guys, so these are the 6 problems, and I think on the actual exam, part 4 was omitted because it was very similar to part 3. So if you guys again want to pause and take a look at these problems to see if you can actually solve this qualifying exam, please do so. Alright guys, let me show you my solutions and let's see if you guys got the same thing. Alright, what's up guys? So I'm going to talk to you about my solution for this problem, and I'll quickly go over it. So I just put up the schematic and I've highlighted the control volume for which I'm going to analyze. So for the first part of the problem, basically the large mass M is 0 and they're asking for the compression temperature first and then the work transfer during the process and the efficiency. So I'm going to go over this quickly. So first we look at the first law of thermodynamics and control volume. Then we say that the heat is 0 because it was given in the assumptions. So we're left with mCv dt equals minus PdV. We use the ideal gas law for this problem. We take the differential of the ideal gas law. And now what we do is we substitute equations 3 and 4 into equation 2. Just some algebra here. Lastly, we know that Cp equals to Cv plus R and Cp divided by Cv is equal to gamma. So we can then integrate equation 5 to get the compression temperature. T2 equals T1 times P2 over P1 raised to gamma minus 1 over gamma. Boom. All right. Now let's look at the work transfer. So again, we go back to the first law. And if we actually integrate the second equation, we see that it's mCv T2 minus T1 is equal to work. And we already know T2 because that's a compression temperature that we got earlier. So all we have to do is just plug it into equation 7 and boom, that's work transfer. So now lastly, we want to look at the efficiency of this process. And the efficiency is 1 because this is an isentropic process. So now, okay, let's go on to the second problem. Now for the second problem, we actually are considering the thermal mass in addition to the ideal gas in the control volume of analysis. So, okay. Now again, what's the compression temperature? So again, we look at the first law, but this time for the internal energy term, we now have the thermal mass as well as its heat capacity. So again, from earlier, we know equations 3 and 4. So we again plug all this into equation 9, basically the ideal gas law. And now we integrate equation 10. And boom, this is a new compression temperature. So it looks very similar to the answer that we got in the first problem statement, except the ratio is now mR divided by mc plus mcp. Okay, so now let's again just look at the work because at the end it asks us for efficiency. So again, we integrate the first law, and we know T2 from the previous slide. And we pretty much all we're doing is just algebra at this point. And you can see that's also very similar to the first work term that we got in the first problem when we did have a 0 value for the large thermal mass. So now what about the entropy generation? So this time we're actually going to use the second law. And recall that this is an adiabatic process, so that the dq over t term is 0. So now for the entropy generation, we actually look at the entropy change for the thermal mass as well as for the ideal gas. And these terms you should know as they are the entropy change for a thermal mass and ideal gas. So, okay, what we can do is that we know the compression temperature, which is T2. That was the first part of the problem. And all we have to do is just substitute it into equation 18. And upon substitution, we actually see that all these terms will cancel out and that entropy generation is actually equal to 0. And therefore, the efficiency is 1 again because this is also an isentropic process. Now let's go to the third part of the problem. So basically what it's saying is that the compression process is really fast, and thus the interaction between the thermal mass and gas may be considered a two-step process. So what's going on is that first we have quickly adiabatic compression of the gas, and then we have thermal equilibration of the gas and the thermal mass at a constant pressure. So this is a constant pressure process. What is the compression temperature, and again, how much entropy is generated? So this is actually quite straightforward. So basically, first, the gas is undergoing adiabatic compression. So the temperature of the gas, let's call it T2 prime, is just very similar to what we got in the first problem. So now we want to use the first law for the second part of the compression process at a constant pressure of P2. We use the first law. So now we also use ideal gas law and we plug this into equation 21 and we end up with this equation. Now you can see that the dt terms are not equal, and that's kind of because they represent the final change. And now for the thermal mass is T2 minus T1 because T2 is the final temperature and T1 is its initial temperature. Now recall that in the problem statement for the ideal gas, again, we know that T2 is the final temperature, but we use T2 prime instead of T1 because in the beginning we have such a fast compression process that its initial temperature, so to speak, is this T2 prime. So all we're doing right now is us solving for T2, and we know T2 prime, so that the compression temperature is actually given as follows. It's a little bit messy, but again, this is very straightforward. So now we want to calculate the entropy. Again, we use a second law, and again, recall this is an adiabatic process. So recall that this is a constant pressure equilibration, so that means that P2 equals P2 prime, so that means this term goes to 0. So basically, you do a bunch of algebra. You plug equation 24 into 26, and you solve for S generation. You know that this is greater or equal to 0, and you have pretty much a huge equation. A little bit of messy. So now we go to the fourth part of this problem. Very similar to this previous part. Again, so basically the system has come to the equilibrium described earlier. But now what happens? But now the reverse effectively happens. We have a fast expansion process to pressure P1, and then this step is followed by thermal equilibration at a fixed pressure P1. What is the final temperature and how much entropy is generated in this process? So basically it's a reverse of problem 3. Instead of the expansion, we now have the two-part compression process. So again, the T3 prime is kind of like the temperature of the gas after the quick the quick expansion. It's given as follows. So now again we use the first law, but at a constant pressure this time of P1. And again, we solve for the final temperature of T3. We know T3 prime and we know T2, and basically we plug all this in together to solve for T3, the final temperature, and it's given as follows. Again, very straightforward. So now we want to calculate entropy. Again, it's kind of messy, and for the interest of time and the interest of space on this page, I'm just not even going to bother. But basically, you plug equation 28, 32, all into 33 for Sgen, and that's the solution. So now for the fifth part of this problem, it's asking us for the efficiency of the round-trip process described by 3 and 4. Now, if you recall in the problem statement, the efficiency is defined as the work from 2 to 3 divided by the work from 1 to 2. So recall that the work from the processing 2 to 3 is given by the first law. Similarly, the work from 1 to 2 is also given by the first law. And basically, we plug all the equations that we know from parts 3, 4, and we use equation 35, 36, and we do a bunch of algebra. And ultimately, we're left with the equation 37, the efficiency of this round-trip process. And this is what I got. Now, for the last part of the problem, basically what happens is that, it's asking us for the practical implementation of this scheme and identify the losses in the practical implementation. And in reality, what happens is that you're pretty much out of time, and hopefully you have done your best and that everything you've done so far is correct. But yeah, this was actually a problem in the real qualifying exam. So actually look at the real qualifying exam, and even though the problem statement that I've shown you guys say that it's an abridged version, in reality, it's actually the full version. So all these problems were in the exact qualifying exam. And when I was studying with my study group, we saw a bunch of different problems, and the difficulty ranged from year to year. And the general consensus on this problem was that, it was quite straightforward and relatively not too complicated. So I would give it a difficulty scale of maybe 1 to 1.5 out of 4 scale, where 1 is the easiest and 4 is extremely difficult. So how did you do? Leave a comment below, and please give this video a thumbs up and subscribe if you like this type of content, and I'll see you guys next time. Peace.